Slightly unusual kind of talk because normally people in academia give talks about work which they've already done. Today I'm not going to talk about work which we have done, but rather work which we hope to do, looking at a few very interesting data points which are already out there in the world, in the industrial and research setting. Right? So I'm going to talk about EV charging, but with a twist, wireless EV charging, and what is the current state of the art and what are some of the challenges and what can we do differently. So wireless power transfer it's a fancy word for something very, very common. For example, we are all familiar with our wireless toothbrush. We put it on the dock and it charges, right? Moving up to fancier applications, you see phones being charged wirelessly these days. This is a concept image from the company Vitricity, which is based in Boston, where there is wireless EV charging happening over here. The charging coil is below. I'll talk more about this. Of course, with buses also we are seeing this. There are various examples in, I think, Norway and Japan where they're charging buses wirelessly. And something even more futuristic, EMROD, which is a company in New Zealand, and they are able to do long-range wireless power transmission over distances of not meters but kilometers. Okay. And they have working demos that are there. The technology for this is very different from the technology for wireless EV charging. So I'm going to limit myself to wireless EV charging. Okay? Physics is similar, applications are different. Now, to make matters very concrete to begin with, rather than starting with some elaborate theory, I'm going to tell you a little bit about the current best solution which is there from Boston, which is Vitricity, which is, this is a clip from one of their YouTube videos where they have a fleet of these cars which just drives into the parking lot over here, and there is the power source over here, there's the charging coil over here, and at the bottom of the car there is another charging coil over here. Right? So this is how they do their wireless EV charging. Efficiencies are quite high. They claim about 92% efficiency. This efficiency is relative to if I had a wired charging. So it's quite good. And they claim that with this is done on a BMW version where they're able to charge the full capacity of the battery in 3.5 hours, which is pretty good, right? Now, what is the technology behind this? So I'm not going to go into great detail about it, but let's start with something many of us are familiar with, right? We've all studied this maybe in class 12, right? This is just an iron core. I put 2 windings around it and I'm able to generate a magnetic flux through the iron core, which transfers energy to the secondary coil, right? This is the traditional idea. We all know that if I remove this iron core from here, everything falls apart. You get almost nothing that is going across to the other side. So I need to get rid of this iron core if I have to do a wireless charging. Right? So this is where this technology comes in, which is called strongly coupled magnetic resonance, where in addition to these wires, I add a few capacitors, both on the primary and on the secondary side. Now, when I add a capacitor and an inductor from class 12, we know, makes a resonant circuit. So think of it like this is one guitar and this is another guitar. If I pluck a string on guitar 1 over here, assuming I have a nearly similar guitar on the other side, that second guitar starts also vibrating a little bit at the same frequency. So that's essentially the same concept that is happening over here. I no longer need an iron core to do the transfer. Okay. So this is a very simple working demo which the group had demonstrated. Here you have a couple of transmit coil with the power source, a receive coil, there is no air, and you're able to transfer power at a particular frequency. So this is very, very roughly at a high level, this is the physics underlying this technology. Now, what are the major issues that this technology has? Right? So one is that as you start bringing this coils closer to each other, or if you try to push more power through it, the coupling between these coils, it begins to increase. Now, as it begins to increase, when you had one single frequency, life was good. This resonance now splits into 2 frequencies, as you can see over here. You have, as you start increasing the coupling over here, you get 2 different modes that emerge. As a result, the efficiency of your power transmission takes a big hit. So there is a limitation on how much power I can transfer. So if I wanted to charge a bus instead of a car, this is going to run into an issue. The second very, very major issue is that the optimum transfer of power happens only in a specific zone of distance. So if it's, in the case of vitricity, it is about 20 to 25 centimeters. If I get it too close, if I take it too far, the power transmission efficiency drops drastically. So this is one of the disadvantages. We are going in for wireless charging for one of the primary reasons is convenience. Now, I don't want to have some elaborate docking mechanism which ensures that I enter within the specific zone of distance. So we need to have a larger room for moving my vehicle around, right? The setup is also very, very sensitive to misalignment. So if I did not drive directly over here, if I was off by, let's say, 10 to 20 centimeters, again, the efficiency drops. Now, we are talking about power in the range of kilowatts. And imagine that, I have, just for sake of argument, assume that every EV was being charged wirelessly. And because of misalignment and such issues, instead of charging at 90%, I'm charging at, let's say, 40% efficiency. The amount of energy that we are wasting due to this, our desire for convenience, it's not really right. Because then you just may as well plug in the charger and get it right. So you want something that can correct for all of these things, right? The other thing is one of the disadvantages or sort of restrictions one should keep in mind looking at models which work in the Western world is how do you make them India specific? So in their case, as you saw in the picture I showed you previously, they had the charging coil between the front two wheels at the bottom of the car. The price point which they have is about $500 is the aftermarket value of the attachment for which needs to be put there. And the charging station itself was about $2,000. So $500 is, let's say, 35,000, 40,000 rupees. Do I really want a 40,000 rupee aftermarket attachment sitting above at the bottom of my car, and post monsoon I go over some piece of road and that's the end of 40,000, right? That would be a terrible solution. Maybe someone who drives a BMW may not worry so much about it, but there's no way I'm going to make an inroad at the base level, let's say our Tata Nexon EV, right? So this is something for us to think about. Is that the best place? Are there other places that we can think of which are more robust for Indian conditions? So that's something to keep in mind. So how can the situation be improved? There are basically two approaches. One is, one sec, oops. Right. My slides order seems to have been messed up when I exported it to PowerPoint. Okay, so let's talk about, can we go back? No, I think, can we switch to my presentation? Yeah, with my laptop. Yeah. Okay, my back. Apologies, my export has not worked. And how can it be improved, right? So there are, roughly speaking, two solutions which have been proposed. One is that, as I mentioned earlier, that as I start pumping more power, the frequency splits into two. So one very, very technical solution is to use what are called non-linear resonant circuits. So you add more complexity to the problem to solve an already challenging problem. That's solution one. Solution two is sort of a real game changer in my mind, which is the advent of metamaterials, or artificial materials, where you, as I will talk more about it, you don't get into this area of non-linear circuits. You do something very, very different. Metamaterials are not just restricted to electrical engineering or electromagnetics. There are people who use acoustic metamaterials. So it's a very general concept, which I will talk about. So these are the two solutions which you can use to get out of misalignment issues, power issues, and so on. Okay. So what are metamaterials? Now this is a slightly busy slide, so let's go over it one by one. So here there are sort of four quadrants in this diagram. You have the first quadrant over here, which is called as DPS, which is double positive. Okay, so what does that mean? So this is a material like glass, wood, brick, whatever. I send in a wave, some energy gets reflected, some energy gets transmitted. This is from our high school optics experiments. And all naturally occurring materials happen over here. This is epsilon, which is electric permittivity, and this is mu, magnetic permeability. Now, it turns out that I can engineer materials to belong to these three other categories. So category 1, as I mentioned, is conventional. Category 2 is what is called a negative permittivity material. A negative permittivity material is not going to allow any energy into the system, and you just see reflection. Which also means that if you calculate the permittivity, it's actually negative, which is very strange. Material 3 is negative permeability. And over here, again, there is no transmission inside the medium. The energy just gets reflected off. And this mu factor is less than 0. Now, the really bizarre set of materials happen over here. When I combine number 2 and number 3, I get these so-called double negative materials. These double negative materials are very, very counterintuitive. Now compare region 1 and region 4. In region 1, this was a glass prism. I sent in light, it got refracted and reflected. Over here, look what is happening. I'm sending light from here through this metamaterial glass prism. Instead of getting refracted in this direction, it's getting refracted in the opposite direction, which is very strange. The reflection, instead of going off here, it's going off in this direction. So this is what is called a negative refractive index material. It is not naturally occurring. You cannot go drill some part of the earth and pluck out this material. This is artificially engineered. And this gives these strange properties. These materials were postulated in a 1960s paper by a Soviet physicist. And it's only around 2007 that they were experimentally made in the lab. Right? So it sounds like magic. So I'll just tell you a little bit about how this happened. Okay? So I already mentioned this, that this is not a bulk material that you can just mine from the bottom of the earth. Right? So you are making this material, you're composing this material out of many small so-called unit cells. At the bottom, you can see I've taken these split rings and these cylindrical metallic posts over here, right? And what I'm doing is, these unit cells are very, very tiny as compared to the wavelength of the radiation that's falling on them. So I can engineer these properties by playing around with these unit cell properties. Now the red arrow over here represents roughly one wavelength of the radiation that's falling on it. This one wavelength contains within it several periods. For example, maybe say 10 to 15 such periods are within this. The electromagnetic wave does not see an individual unit because that individual unit is so small. It instead sees a kind of a average behavior. And since it sees an average behavior, I can engineer, for example, the radius of these coils or the height of these posts, and I can alter the mu and the refractive index can be tuned in this way. So this is what is sort of what is happening underneath the hood. There is resonances that are happening over here, and the electromagnetic wave does not see the individual unit, it sees a net effect, and that is what we are leveraging over here. Now, natural question, is this totally new for the sake of EV charging? The answer is no. This concept is already being used to make flat lenses. So here is a conventional material. So if I have a bunch of light which is coming from the left, I want to focus it to a point on the right. We've all also done these optics experiments in school. I take a convex lens and light focuses here very well. If I make a flat lens out of this, I don't get the focusing effect. That is also very clear, right? When I look out from my glass window, I see outside exactly the way it is. I don't see enlarged or a shrunk view. I see what it is. So using a flat lens makes no sense if I'm using a conventional material like glass. But because I can play around with the refractive index at will, I can actually create a metamaterial flat lens. So this has huge implications for example, cell phone manufacturers. I can make a flat lens, make my entire body of my cell phone very, very flat. I don't need anything else. To fabricate it is also very easy. Right? So this is already there. The other very, very cool application is invisibility cloaks. This sounded like science fiction maybe 10 years ago, but it's not anymore. It has been demonstrated. I think this is from 2007 that this work has been done at Harvard, where here is your traditional object. Think of the yellow thing as a radar. The radar illuminates this thing, you see the reflection, and that's how you detect the object. You know that there is, let's say, an enemy aircraft over here. But with this invisibility cloak, which is made up of these metamaterials, the wave just bends around this object and goes. And what I'm doing is I'm playing around with the refractive index because I have a control over it. I could make it negative, I could make it less than 1, all sorts of strange things are possible, and I can make this. Now, there is a lot of fine print to it, which is why you don't see people roaming around in invisibility cloaks. There's a lot of very serious engineering that goes behind it. It's very frequency selective. So you may be transparent at one frequency, and at a slightly different frequency, you're not transparent. So for our vision, because we see a range of say 400 nanometers to 700 nanometers, being transparent at one frequency is not good enough. I have to be transparent over the entire spectrum. But those are engineering challenges. Maybe 10 years from now, that will also be there, right? So we're using this idea, we are transplanting this idea into the world of EV charging. So how is it going to help us in EV charging? So this is sort of the setup that we're thinking of. Here is our source, the transmit coil, the receive coil as before. What I'm doing is I'm introducing this metamaterial sheet in between. So what does that do, right? I can increase all these three things. I can increase the efficiency, the charging distance, and the misalignment tolerance. And this diagram really explains it. So let's go over it one by one. So imagine I had no metamaterial sheet in between. So the magnetic field kind of diverges away from the transmit coil, as you can see by the black arrows. That's how it's traditionally done. The moment I put this metamaterial sheet in between, you can see that these dark blue and the red lines, that energy is being focused. So if this were light, you would say, oh, I've just put a lens which is collecting all of the light. But now I'm doing the same thing with electric and magnetic fields. I'm focusing them into the receive coil. So I can also, if I put series of these things, I can increase the alignment distance and also the collection efficiency, right? There is a lot of work already in progress. There are special issues that are, people are writing long papers reviewing the tech behind it. There are experimental demonstrations, as you can see over here. There are several different topologies. So here, this is the simplest one where I put one lens in between. I could put several lenses. I could put lenses on opposite sides and still have this effect happen. So it's in a creative sphere, there are a lot of options. It's just not that you have to put only one lens. There's a lot that you can do, right? And this graph sort of shows that the efficiency, how it increases. The red line is the efficiency increase with the presence of this metamaterial lens as compared to the conventional wireless charging scene without the lens. So you're already seeing a huge improvement in efficiency. In excess of 90% is possible, right? People have also worked out that you can misalign the transmit and receive coils and still get a very good transmission. So I think since I'm low on time, I'm not going to explain these graphs, but you can do pretty well even with misalignment. Okay. So what are the challenges and opportunities that I see particularly in the Indian context? As I mentioned, efficiency has to be greater than 90% at the very minimum. Otherwise, you're wasting a tremendous amount of energy. And if you're really talking about things like net zero, then you cannot be wasting energy where a simple wire would do. Vehicle coil, should it be built into the design of the EV? That sounds nice, but then maybe that's a huge challenge for a car maker. Or should it be an aftermarket part, right? Location of the coil, should it be at the bottom? Can we think of it being on the top? And the docking station is just on the top. A car just drives below and there's enough gap for us to have safety. Or maybe on the side. Could it be that I plug it into the fuel port, which current EV chargers have? I plug an adapter over there, like I have the USB antenna, right? These are questions, of course. And the location of the metamaterial slab. Should I make it part of the car or should I make it part of the charger? So these are questions outside of technology, right? More to do with economics, which will dictate the solution. So our vision, so the expertise of my group is in electromagnetic modeling, and we hope to be able to design metamaterials for these applications. And that's only a part of the story. We're to fuse with existing efforts for not just wireless charging, but charging of EVs in general, both at IIT Madras Research Park and industry folks that are over here, and come up with India-specific designs, implementations, use case scenarios, and protocols. So that's how I see this field going forward, and I'd be happy to collaborate with any of you who are also similarly interested in this area. So with that, I'd like to conclude my talk.